A sequence is a succession of numbers arranged according to some rule. Another term for sequence is progression. A sequence is a function whose domain is a set of positive integers. Each number in a sequence is called terms. For example, the triangular numbers 1, 3, 6, 10, 15, 21, and so on can be denoted as follows. A sub 1 for the first term, which is 1, a sub 2, which is 3, a sub 3, which is 6, a sub 4 equals 10, a sub 5 equals 15, and a sub 6 equals 21. So in general, to find the nth term of this sequence, we use this rule. A sub n equals n over 2 times n plus 1. So we use this formula to determine the next term or any term of this sequence, the triangular numbers. The sequence whose terms continue indefinitely is called an infinite sequence. Infinite sequence is specified by listing the first few terms followed by an ellipsis. If after a certain term the sequence stops, the sequence is finite. Let us have some examples. Find the first four terms of the following sequences given by letter A sub n is equal to n plus 2 times n plus 3. B, a sub n is equal to negative 1 raised to n over n plus 1. Since we are to find the first four terms, we let n be equal to 1, 2, 3, and 4. So for letter A, when n is equal to 1, a sub 1 is equal to 12. 1 plus 2 is 3 times 1 plus 3, which is 4, and 3 times 4 is 12. When n is equal to 2, a sub 2 is 20. 2 plus 2 is 4, 2 plus 3 is 5, and 4 times 5 is 20. When n is equal to 3, a sub 3 is 30. 3 plus 2 is 5, 3 plus 3 is 6, and 5 times 6 is 30. And when n is equal to 4, a sub 4 is 42. 4 plus 2 is 6, 4 plus 3 is 7, and 6 times 7 is 42. So the first four terms of this sequence are 12, 20, 30, and 42. We do the same process for letter B. Replace n by 1, so a sub 1 is negative 1 half. Negative 1 raised to 1 is negative 1 over 1 plus 1 is 2. When n is equal to 2, a sub 2 is 1/3. Negative 1 raised to 2 is positive 1 over 2 plus 1 is 3. On the other hand, when n is equal to 3, a sub 3 is equal to negative 1/4. Negative 1 raised to 3 is negative 1 over 3 plus 1 is 4. And when n is equal to 4, a sub 4 is equal to 1 over 5. Negative 1 raised to 4 is positive 1 over 4 plus 1 is 5. So the first four terms of this sequence are negative 1 half, positive 1/3, negative 1/4, and positive 1/5. Take note, the factor negative 1 raised to n causes the signs of the terms in a sequence to alternate between negative and positive depending on whether n is odd or even. How about if we were to find the rule or write a mathematical expression for the general nth term of a particular sequence? For example number 2, write a mathematical expression of the following sequences. For letter A, the sequence 1, 4, 9, 16, 25, these are squares of counting numbers. 1 raised to 2 is 1, 2 raised to 2 is 4, 3 raised to 2 is 9, 4 raised to 2 is 16, and 5 raised to 2 is 25. So the general nth term is a sub n equals n squared. You can determine the other terms in the sequence using this rule. For letter B, the numerators are all equal to 1, but the denominators are counting numbers increasing consecutively from 1, 2, 3, 4, 5, and so on. So a sub n is equal to 1 over n. For C, these are powers of 2. 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, 2 raised to 4 is 16. So we have 2 raised to n. However, the terms are powers of 2 with alternating signs. Negative positive, negative, positive. Remember, this factor -1 raised to n causes the signs of the terms of this sequence to alternate between negative and positive. So we must multiply this value to this factor. So the general nth term of this sequence is a sub n equals -1 raised to n times 2 raised to n. The sum of these terms can be expressed as 1 plus 4 plus 9 plus 16 plus 25, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. This sum is an example of a series. It is the indicated sum of the terms of a sequence. Infinite series is the sum of an infinite sequence, and finite series or partial sum is the sum of the first n terms of a sequence. A convenient way to express a finite series or partial sum is the summation notation or sigma notation. Summation notation is the sum of the first n terms of a sequence represented by this. This is read as the sum of a sub I as I goes from 1 to n is equal to a sub 1 plus a sub 2 plus a sub 3 and so on a sub n, where I is the index of summation, 1 is the lower limit, and n is the upper limit. The lower limit tells you where to begin the sum and the upper limit tells you where to end the sum. Examples. Letter A. Evaluate each sum. Number 1. The sum of 2i as I goes from 1 to 5. The lower limit is 1 and the upper limit is 5. That means we need to replace I with 1 to 5 and simplify to get its sum. So we have here 2 times 1 plus, we start at 1 because that is our lower limit, followed by 2 times 2 plus 2 times 3 plus 2 times 4 plus up to 2 times 5 because our upper limit is 5. Simplify, we have 2 plus 4 plus 6 plus 8 plus 10, which is equal to 30. So the sum of 2i from 1 to 5 is equal to 30. Number 2. The sum of -1 raised to I over I as I goes from 2 to 6. Lower limit is 2 and upper limit is 6. So we will start replacing I with the value 2 and end at 6. So 2, 3, 4, 5, and 6. Simplify, -1 raised to 2 over 2 is positive 1/2, -1 raised to 3 over 3 is negative 1/3, -1 raised to 4 over 4 is positive 1/4, -1 raised to 5 over 5 is negative 1/5, and -1 raised to 6 over 6 is positive 1 over 6. And this is equal to 23 over 60. Another example. Write each summation notation in expanded form, then find its value. Same process, determine first the lower and upper limit, then simplify. Number 1, the lower limit is 1 and the upper limit is 6. So we replace I with 1 up to 6, then find its sum. -1 raised to 1 times 2 times 1 is -2. -1 raised to 1 is -1, and 2 times 1 is 2. So -1 times 2 is -2. -1 raised to 2 times 2 times 2 is positive 4. -1 raised to 2 is positive 1, and 2 times 2 is 4. So 1 times 4 is positive 4. -1 raised to 3 times 2 times 3 is -6. -1 raised to 3 is -1, and 2 times 3 is positive 6. So -1 times positive 6 is -6. -1 raised to 4 times 2 times 4 is positive 8. -1 raised to 4 is positive 1, and 2 times 4 is 8. So 1 times 8 is 8. -1 raised to 5 times 2 times 5 is -10. -1 raised to 5 is -1, and 2 times 5 is 10. So -1 times 10 is -10. -1 raised to 6 times 2 times 6 is positive 12. -1 raised to 6 is positive 1, and 2 times 6 is 12. So 1 times 12 is 12. Recall that this factor causes the signs of the terms in a sequence to alternate between negative and positive. So -2 plus 4 minus 6 plus 8 minus 10 plus 12 is equal to 6. So this is how you expand a summation notation, and the value of this notation is 6. For number 2, the sum of 4k minus 1 as k goes from 2 to 8. The lower limit is 2 and the upper limit is 8. So replace k by 2 up to 8 and find the sum. 4 times 2 is 8, minus 1 is 7, plus 4 times 3 is 12, minus 1 is 11, plus 4 times 4 is 16, minus 1 is 15, plus 4 times 5 is 20, minus 1 is 19, plus 4 times 6 is 24, minus 1 is 23, plus 4 times 7 is 28, minus 1 is 27, plus 4 times 8 is 32, minus 1 is 31. And 7 plus 11 plus 15 plus 19 plus 23 plus 27 plus 31 is equal to 133. Letter C. Express each series in summation notation. Now, to determine the summation notation of this series, we first need to find the rule or the general nth term or the mathematical expression of this sequence. Number 1, we have 7, 14, 21, 28, 35. We get these values by multiplying the counting numbers by 7. 7 times 1 is 7, 7 times 2 is 14, 7 times 3 is 21, 7 times 4 is 28, 7 times 5 is 35. This indicates that each term of the series can be written in the form 7i. The index starts from 1 to 5. Thus, the series, written in summation notation, is the sum of 7i as I goes from 1 to 5. Number 2, these are cubes of counting numbers and can be written in the form I raised to 3, where I starts from 1 to 6. Therefore, the summation notation is the sum of I cube as I goes from 1 to 6. Take note, you can use any variable other than I. Number 3, we get these values by multiplying the counting numbers by 3, represented by 3k, where k starts from 1 to 5. So the summation notation is the sum of 3k as k goes from 1 to 5. And that is all about series.